Cool. So last time we talked about sequence modeling. This time I'm going to be talking about attention and transformers. Attention and transformers are kind of like the basis of most of the models we use nowadays. So I'm going to go through them and go through some fundamentals. And this also will be the thing that you're implementing in the first assignment. So, if you have any questions, please feel free to ask. So, yeah. So last time we talked about recurrent neural networks as sequence models. And the problem with recurrent neural networks was essentially that they had vanishing gradient problems. Also, you're trying to fit, a long sequence into a single vector. And because, sorry, I feel like I'm missing a slide here, but because you're trying to encode each long sequence into a single vector, if you have a very long sequence or a very short sequence, they both kind of become one vector. And because of this, it's hard to efficiently encode all of the information that you need in these variable length sequences in an efficient way. And so the basic idea behind attention is that we want to encode each token in the sequence in a vector. And then when generating the next output, perform a linear combination of these vectors weighted by attention weights. And the basic idea behind this is that because you're encoding each token as a single vector, each token has approximately the same amount of information, especially if you're doing subword segmentation, like you have longer tokens and shorter tokens, but they end up being, corresponding to a single coherent piece of information. So we just to give an example of what this looks like, we have a few types of attention. The first type is called cross attention. And cross attention is used in models like encoder-decoder models, where you have encoded content in the input. And when you generate the output, you want to attend to the encoded content, the encoded input. And this was kind of the first variety of attention that was proposed. So if this is our input here, it's a Japanese sentence, and we want to generate the word this, we will want to focus on the Japanese word that corresponds to the word this. So this was the Japanese word that means this. And so what we would do is we would take the encoded vectors for all of these, and we would turn this into a single vector here. And then when we generate the word is, we would want to attend mostly to the word, the Japanese word for is, which is this one. If we're generating a word that doesn't really correspond to any word in Japanese, for example, we would kind of maybe attend more generally to the whole sentence and generate based on the previous words. And then, we would do it again for the word example. Another variety is self-attention. And self-attention is when you're allowing a sequence to attend to itself. And the reason why you might want to do this is because words or tokens take their meaning in the context of the other tokens in the sentence. So, for example, one easy way to think about this is if you think about the word run in English, how many people here speak some other language? Probably, I guess, most people. Some people don't. Even if you don't speak another language, you can think of the different meanings of the word run. But if you speak another language, think of the number of different ways you could translate the word run into your language. It's probably different ones for like running a race, running a company, running a computer program, a run in a stocking. So there's lots of different meanings, and which one you take depends on the context. So if the words are relatively independent of the context, you might not really need to attend to the other words. But for example, the word is another example of a word that gets translated a lot of different ways. So if we were solving a machine translation problem, we would want to attend to all of the context to figure out how we would be translating this word. So the way we calculate attention is, this is an example of cross attention. So this is an example where we have an encoded input that's encoded according to any sequence model. For the purpose of argument, let's say this was encoded according to a bidirectional RNN or something like that. It doesn't necessarily need to be encoded according to attention. And so then we have these vectors here. We also have a vector based on all of the previous output that we have generated. And we use a query vector. And what this query vector is it's a vector that tries to decide which of the encoded vectors to pay attention to. We have a whole bunch of key vectors. And these are the key vectors that help us look up the vectors in the encoded sequence. And for each query key pair, we then calculate a value, a float. And the basic idea is that we'd like the floats to be larger for the stuff that we should pay attention to, and the floats to be smaller for the stuff we shouldn't be paying attention to. And so in the case of this example, the next word here would be this. I hate this movie. And so this Japanese word here, kono, corresponds to the word this in English. So you'd want it to have a higher attention value. You can then normalize using a softmax so that they add up to 1. And this gives you something that looks like a probability over all of the outputs. In reality, it doesn't have to be a probability. It could be something that doesn't add up to 1. Like, for example, you could take not the softmax, but a sigmoid, and you would still be able to calculate attention. But in reality, most people use a softmax just because it allows the different words to compete with each other for attention and calculate the outputs. So after we do this, we have a concept of value vectors, and we need to have one value vector for each attention weight that we have calculated. And what we do is then we take the weighted average of, or we take the weighted combination of the value vectors to calculate a new vector. And so, you know, we'd multiply this one by 0.76, this one by 0.08, and then add all of those together to get a new vector. And this sort of attention operation, it's a kind of atomic operation that you can use in any part of the model that you would like. You could use it, usually we use it for sequence encoding or decoding, but you could also do attention over, for example, some sort of knowledge base that you have or other things like that. One other thing that I forgot to mention on this slide is that's very important is this function is the same function regardless of the query and key vectors that you feed in. So it has to be a function that takes in one query vector and one key vector. And the reason why is the same reason we use the same function at every time step for RNNs, right? If we use the same function every time and it's not like sequence length dependent, this will scale to arbitrary length sequences. But if we use something that requires like one query vector and 7 key vectors, or one query vector and 4 key vectors, that would work for this sequence, but it wouldn't work for any other sequence length. So we need to make sure that the attention function takes in a query vector and a key vector. So this is an example of cross attention in a translation model. And what you can see is the cross attention in the translation model learns to attend to the words that correspond to each other for French-English translation. So it learns to attend to the one that corresponds to le, accord, sur, la. And then when the word order reverses, it learns to attend kind of in reverse order. When there's not a good correspondence between them, it learns to spread it out a little bit. So this is despite the fact that we haven't used any sort of supervision to learn this. This is just learned kind of naturally in the course of learning the model. But it does learn kind of natural correspondences between them. Any questions so far? I think a lot of people might have heard of this because it's very fundamental in a lot of machine learning nowadays, but. Okay, cool. Let me move on. So the next thing I'd like to talk about is attention score functions. So attention score functions can take a number of forms. But basically, the basic requirement is that you feed in one query vector and one key vector. The first attention score function that was proposed is something called the multi-layer perceptron, or is a multi-layer perceptron. So it's basically a feed-forward network with a single hidden layer. And what you do is you take the query vector and the key vector, you multiply it by a weight matrix, extract features from it. So you do the standard kind of linear transform plus nonlinearity. And then you multiply this by the transpose of a vector to give a single scalar corresponding to the attention weight. So this is a very powerful method because you might have heard in your other machine learning classes, multi-layer perceptrons, like a neural network with a single hidden layer, can calculate an arbitrary function. So this can calculate an arbitrary attention function. And so kind of by default, this is the most powerful possible attention function that you could have if you made it large enough. However, that being said, it's actually not a great attention function. Like it was the first one that was proposed, but it has fallen out of favor for a reason. And the reason why is because there's actually a very simple thing that you cannot calculate with this, but it's a lot easier to calculate with other varieties. And the basic thing that is hard to calculate, it's not impossible because this can approximate any function, but the thing that's hard to calculate is just a dot product between two vectors. And the dot product between two vectors will be larger if the query and key vectors are more similar, and smaller if the query and key vectors are more different. And this is very intuitive. Like if you have words that are similar in embedding space, you would want them to have higher attention values. So this very intuitive thing is actually relatively hard to calculate with the neural network-based attention function. So what we tend to do instead is we tend to do something called bilinear attention. And bilinear attention is basically where you take the key vector and you take the query vector. And you multiply the key vector by a weight, and then take the dot product, or you take the transpose and calculate the output. And so this is good because if we wanted to do the very intuitive thing of making the attention weight higher when the query and key vectors are similar, you can just make this weight vector a identity vector, and you would be able to achieve that. But you're also able to achieve more complex things like rotating the features or doing any sort of linear transform here. So this is very common. This is the type of thing that we use in the transformer with a small tweak. Another thing that was tried previously, but we don't really use anymore, is just taking the dot product between the two vectors. The reason why we don't do this is the multi-layer perceptron is essentially too flexible. So it allows you to do too many things and it doesn't have a strong enough bias. The dot product is not flexible enough because basically it says that the query and key vectors need to be in the same space. And so this is also, not quite good enough for attention. Another disadvantage between it is the query and key vectors need to be the same size. Whereas if you're doing the bilinear function, you can make this a non-square matrix and you can change the size of the vectors. So that's another disadvantage, but the main disadvantage is just the inflexibility of this. Another thing, I mentioned scaled the dot product, but actually I should probably just call it scaling. So another addition that you can add on top of these attention functions is scaling. And basically the way that we normally scale is by taking the square root of the size of the key vector or the query vector. The reason it could be the key vector or the query vector. Usually the query vector and the key vector are the same size, so it doesn't really matter which one you take. But the reason why we do this is if you have a network of size 256 or a network of size 512 or a network of size 1024, what happens is if you don't do this scaling, this value will have a different overall scale. The dot product will have a different overall scale between larger and smaller networks. And so because of this, what happens when you have a different overall scale? Essentially, after the softmax, the distribution gets peakier. So if you have if you have a softmax where one of the values is 1 and the other value is 0, you'll get something like 0.75 and 0.25. This is not, this is not precise. I'm just giving something that's a little bit close. But if you do something that's 2 and 0, you'll get something like 0.9 and 0.1. If you have something that's 4 and 0, you'll get something that's like 0.98 and 0.01. And so the scale of the input values to the softmax affects the peakiness of the softmax. So you would start getting to the point where if you have a very big network, then at the very beginning of training, you could have these very, very peaky values. Or if you have a relatively small network with the same initialization, you could have very flat values, and both of those are bad for learning. So this allows you to keep other parameters relatively constant regardless of the size of the network. If you want a bonus, you can try to figure out why this is the square root. If you like math and are bored by my explanation today, you can think about why this should be the square root and not just something other than the square root. Cool. And if it bugs you and you can't figure it out, I can tell you later in office hours if you come next week. Yeah.
So previously, the transpose of Q by multiplied by K is inflexible, but then so adding the 1 over square root of K stabilizes that? I mean, it still has to be in the same space, right?
Yeah, so actually let me clarify. So this is inflexible. The inflexibility comes from this term here. I should fix my slides, but basically like this scaling is independent of the thing that you have up here. And so if you have this, you probably still want to do scaling by the, or you generally still do scaling by dividing by the square root of K or Q. So if you did this, do you have an idea what you would want to be scaling by? Any ideas? It'd be by the size of the hidden vector here, because the size of the hidden vector would affect the overall scale. So so basically what you want to be doing is you want to be scaling by the number of things that you'd be adding together. So you could add scaling to these two as well. A good question. Are there any others? Yeah.
For the same token, are the query key and value vectors generally very considerably different?
Yeah, so for the same token, are the query key and value vectors different? So in cross-attention, the query value vector will be different because it will be from, like, for example, the output, and the key vector and value vectors will be from the input. Traditionally, usually the key vectors and value vectors are the same. But in the transformer, we run them through linear transforms. So the transformer is using these weight matrices, and I'll get to that in a second. Yeah. Yes.
So in the dot product, you said it's inflexible because the query and key have to be the same.
Mm-hmm.
But when you're using the scale dot product, it might reduce the peakiness of the softmax, but the issue of it being inflexible because the variability have to be the same
Right.
still exists.
Yeah, it still exists. And so this scaling can also be applied to bilinear attention or multi-layer perceptron, and those are less. Yeah. Cool. Okay. So another thing I'd like to talk about is masking. And masking is a way to efficiently implement these models. And basically the way it works is it's very similar to the figures that I showed last time, where the figures that I showed last time talked about which values we use and which values we don't use in making our next prediction. And so when we predict the first word in the output, we want to be able to be attending to all of the words in the input. When we predict the second word, we want to be attending to all of the words in the input and the previous word, et cetera, et cetera. And so what we can do is we essentially mask the attention values of all of the words that we shouldn't be using when we make a prediction. And the way we implement these masks is basically we calculate attention over all of the values, and then we add a negative infinity or negative very large number to all of the values we want to mask out. And so what happens after we do that is we get attention values for all of the ones that we shouldn't be masking out. And for all of the ones that we should be masking out, after we take the softmax, their probability basically goes to 0. And that allows us to efficiently implement this. And the reason why this is good, and actually one of the big advantages of attention-based models over RNN-based models, is RNN-based models, in order to calculate the next input, you need to calculate all the way up to the previous input. So you basically need to have a for loop. You need to have a for loop that steps one by one through the outputs. But for transformers, you can actually turn them into a big tensor. And that big tensor can calculate all of these attention values at the same time. And that's very efficient on GPUs or TPUs or stuff like this. So you'll see this implementation, you'll see the way this is implemented in the annotated transformer that I'll show in a second as well. Cool. Any questions? What's up? Okay, good. So next I want to get to transformers. And these are a specific implementation of a model that uses attention. It's not like a variety of attention. It's a model that uses attention in its kind of core. And basically it's a sequence model, a model that has an encoded input and predicts an encoded output. It's based entirely on attention. And so it doesn't use recurrent neural networks or any other variety of sequence encoding mechanism. It just uses attention. It has strong results on, I wrote machine translation because that's what they did in the original paper, but really everything. And it's fast because it doesn't require any of the incremental processing that RNNs require, as I mentioned before. So there's two types of transformers that we need to be aware of. There's encoder-decoder transformers, and these were the original type of transformer. They're used in semi-popular models like T5 and MBART. And then there's decoder-only models, and decoder-only models only have a decoder. So the encoder-decoder model looks like this. The decoder-only model looks like this. And I'll explain about both of these in turn. So the core concepts in transformers that are not covered by regular attention are positional encodings, multi-headed attention, masking, which I already kind of talked about a little bit, residual layers and layer normalization, and feed-forward layers. And so I'd like to start out from kind of like the beginning of the model and go forward. So the first part of the model is input embeddings. And input embeddings we already know about. They're pretty simple. we generally split up the inputs using subwords, and we use something like sentence piece or tokenization models. And we have an input embedding, and these are just looked up like previously discussed models. So nothing special here. The next thing is multi-head attention. So this is an expansion of attention. And the way it works is by doing different attention calculations for different parts of the model. And the intuition about this is that information from different parts of the sentence can be useful, or sequence can be useful in different ways. So as I mentioned before, run is a very ambiguous word. And if we have, I run a small business, I run a mile in 10 minutes, the robber made a run for it, the stocking had a run. All of these kind of mean different things. But they're different in different ways, right? So the first one is syntax. So the first two are verbs, and the second two are nouns, right? And the way we can tell something is a verb or a noun is we can look at the very neighboring words. And so if something's preceded by a noun, it's usually a verb. If something's preceded by an article or determiner, it's usually a noun, right? And so because of that, to disambiguate between nouns and verbs, we need to look at, very nearby things. To disambiguate the semantics, we would need to look at farther away context. So we need to look at things like, surrounding nouns or verbs or other things like that. And so the way multi-head attention works is, this is also written in the transformer paper, but multi-head QKV is an operation that takes query vectors, key vectors, and value vectors, and runs multiple pieces of attention over it, essentially. So the first thing that we do is we, in the transformer, is we multiply by some weights. And these weights in the transformer are separate for query vectors, key vectors, and value vectors. And I mentioned before that we have bilinear models where we multiply by weights. Where I described it is essentially this. The transformer formulation is like a slight bit different than this. It's essentially, we have WQ, Q. So we're first multiplying by the weights with the query and the weights with the key. And so we have two vectors, but we still have, it's kind of a linear transform. It's like this. And two matrices multiplied together. So multiplied by together also are a matrix. So this is essentially a bilinear. It's a variety of a bilinear. Then we also have weights multiplying by the values. But basically, what this results in is this results in vectors, which are the vectors here, Q for the query, the key, and the values. And then what we do is we split these up into n attention inputs. And so let's say we have two heads and our overall vector size is 4. That would mean we would split it up into two sets of vectors where the size of each is 2. And then we run attention over each of the heads individually, and we get the result of the attention. And then we concatenate them back together. So this is essentially, this is how it works. This is also how it's implemented. And if you look at an implementation of multi-head attention, you'll basically see it's doing the multiplications, then it's resizing the vector. So we go from, or sorry, resizing the matrix. So we go from a tensor of size 4 by 3. So 4 rows and 3 columns. And we go to a tensor of size 2 by 2 by 3. So we have 2 batches or 2 heads. And we have 2 rows, and then we have 3 columns. So you'll see in implementations that will also have this resizing operation, and then we resize back to the original size afterward on calculating. So here's a code example of what it looks like. So yeah, we have the transposing, we have the reshaping to get H heads. And then we apply attention to all of the projected vectors in the batch, and then we concatenate them. Okay, so if we look at what happens when we do multi-head attention, this is an example. This is an example from the original attention paper, and it's looking at cross attention. No, sorry, this is looking at self attention. And so it's calculating the representation for the word making. And making is also one of those tricky verbs, right? Where how you would translate it really depends on the surrounding context. And so we have different heads. We have many heads are pulling in information from more difficult over here, because make more difficult kind of disambiguates how to translate make. But you also have a few that are either focusing on the word itself or focusing on the immediately previous vector here. And the immediately previous one might be pulling in syntax information, like I mentioned before. So kind of the intuition that I talked about here, where it pulls in various types of information with various heads, actually shows up when you go in and visualize. And if you want to take a closer look at this, there's this toolkit called BertViz. This is now very, actually it was updated last year. I was going to say this is now very old, but basically like it allows you to walk through the different layers, different values in the text and different heads. And they have a Colab tutorial where you can go in and play around with it yourself. Cool. Yes.
What's the intuition behind splitting up the inputs instead of feeding the entire input into each head?
Yeah, so good question. What's the intuition about splitting up the inputs instead of feeding the entire input into each head? So for the value vectors, it's kind of obvious, because if you fed the entire input into each head, you would multiply the values by the number of heads, and you would get a larger vector coming out than you had going in, and you kind of want to keep the size the same. For queries and keys, you actually could do that. So you could multiply by like a larger vector and get very large queries and keys and combine them together. And that wouldn't change the size of the input and output. You'd still get the same size output. It would be maybe a richer representation. But I think the only problem with that is just it would take more computation. And so people stick with the size. Yeah. How do you decide the number of heads you use? So this is a really good question about any hyperparameter that you're doing. Like, how do you determine your learning rate? How do you determine your optimizer? Anything else? The answer is number one, try what people have tried in the past. Number two, if you want to fiddle around with it, run experiments. That being said, there are kind of rules of thumb. And if you look at models, generally as they scale up the size of the model, they'll also scale up the size of the heads. Usually it's like more heads as the model gets larger, but there's no really fixed rule. Cool. Yes.
So since the entire thing happens like end of row lines in the transformer,
Yep.
is there ever iteration to the next, or is it always different?
Is there a benefit of changing the number of heads from one iteration to the next? I've not seen people doing that before, so my guess is that there's not enough benefit to do something complex, but yeah, it's a good question. Yeah.
So I can answer the question over here. So the reason why you don't change the attention over here by every time dynamically is that the main problem you need to also recalculate the mask, right? When you change, change all of the for each time. And calculating the mask and generating the mask spend a lot of time. So you need to spend a lot of time doing that. So that's kind of
You need to regenerate the mask when you have a different number of heads.
Yeah. You really based on the input, right? So you have to generate the mask for every time. If you you change the headings for every time, changing all those structures.
Okay, yeah, we could take a look at that in the code example here. Yeah. Okay. Any others? Okay, cool. So next I'd like to go to positional encoding. So for positional encoding, we have here. And the important thing about the transformer model is that it's purely attentional. And because it's purely attentional, if only word embeddings were used or token embeddings, there would be no way to distinguish between identical words. And so if you wanted to attend to big over here and big over here, the query vectors and key vectors would be the same for these two words, right? And that's a problem because you might want to be attending to words that are like locally, that are very close to you, as opposed to words that are very, very far away from you. And so in order to fix this, there are methods that do positional encodings. And positional encodings add an embedding based on the word position. And so if you look at this, you have like big in position 2 and big in position 6. So you would be adding these two things together. And because of this, the embedding of this big and the embedding of this big would become different. And so now you can distinguish between them. And yeah.
Is there a reason that I did not calculate it? Taking that support obvious architecture.
Is there a reason why they're added and not concatenated, you said? Yeah, so that's a great question. So it's a question that I hear a lot about, like adding any sort of auxiliary information into a model. It doesn't just have to be position encodings, it could be anything else. And so let's say this is size, let's say this is size n, and you want to get an output of size m. So if you would be doing this concatenated, you would need a matrix that's m by 2n to calculate the outputs. And so that doubles the number of parameters you need here. Also, another way you can think about it is this is the left side. If this is the left side of the weight matrix, and this is the right side of the weight matrix, if you add them together, it becomes equivalent to this in the case that the left side of this and the right side of this are equal. And so actually, basically what concatenation, what adding them together is it's concatenating them with the constraint that the parameters here are equal. So is that a good thing? It certainly makes it less flexible, but it reduces the number of parameters. And basically they're betting that added flexibility is not good enough to, make the additional number of parameters, require the additional number of parameters. Cool. So the first variety of this is called sinusoidal encoding. And the way it works is you calculate each dimension with a sinusoidal function. It looks like this here. So we have the sine of this times the times t. And this is 1 divided by, I mean, this could be something else, but in the original paper, this is 1 divided by 10,000 exponentiated by 2k divided by d. And this is just to give a little bit of an intuition about what this looks like. This means that you have values that at the lower values of k, very, very quickly, they kind of change very quickly with your position. But at the larger values of k, they change very slowly with position. So the motivation behind this, the reason why this was done originally, is actually if you look at the dot product between two embeddings, it becomes relatively high if they are closer together. And so kind of the motivation for this is this gives you a strong kind of bias towards, at least at the very beginning, attending to things that are close together. And the other option is, another option is learned encoding. And learned encoding basically just initializes a single encoding for each position and learns it together with the model. The advantage of this is this gives you more flexibility. The disadvantage of this is this makes it absolutely impossible to extrapolate to new links. So at least in this, like let's say you wanted to do new links, let's say you wanted to go to t that was larger than any one you used in the training data, at least theoretically, you could just extend the positional encodings and use something that you had, and calculate something that you had never seen before in the training data, which would not be possible for the learned encodings. However, in reality, it doesn't actually work very well because the model has never been trained on longer sequences, so it kind of doesn't know what to do with them. And so that is that's an issue. There's also relative encodings, and relative encodings are now a very important part of our transformer models. Absolute positional encodings, what they do is they just add an encoding to the input and hope that the relative position will be captured. And that's not a horrible, assumption, especially if you specifically craft them so that the dot product between embeddings kind of is close for close ones together. But the other option is relative positional encodings that explicitly encode the relative position between the two things that you're attending between the query vector and the key vector. And the most popular variety of relative positional encodings right now is something called ROPE, or rotary position encodings. And the basic idea behind it is that you want the dot product of the embeddings to result in a function of relative position. And so this is the fundamental assumption. So you have the function that generates the embedding for each of these. You take the dot product between them, and you get a function that depends only on the difference between the two. And the reason why this is good is because this kind of enforces a strong constraint that all attention is kind of biased by relative positions as opposed to absolute positions. So ROPE is very involved, and I don't want to go through all of it in class because it would take a lot of time, and it's kind of better to go through the materials that you can read. But in summary, it uses trigonometry and imaginary numbers to come up with a function that directly satisfies this property. And the way this function works, or the way this function is calculated, is you have the regular vector here, and the regular vector is multiplied by this cosine m theta 1, theta 2, theta 1, theta 2, theta 2. And then you have this kind of rotation, this thing that rotates these two elements here, rotates these two elements here, and negates the first one, multiplied by a sign. And this ends up resulting in a function that looks exactly like this. So basically, the idea is it worked back from a desirable property that you wanted the function to have and came up with a function that allowed you to realize this. Cool. I know this is brief, so you'll have to go in and dig into the math to fully understand this if you want to, but are there any high-level questions? One thing I should point out is if you look at this, you might believe that this would suddenly solve a lot of problems. It's like, oh, suddenly this will solve extrapolation to very long sequences because we only depend on the like relative positions. So it doesn't matter if I only train on 512 tokens. It should be able to, very elegantly generalize to, 10,000 token sequences. But in reality, that's not the case. The reason why it's not the case is because there are other ways other than positional encodings for the model to figure out what position something is in. So to give an example, if you are if there are no tokens previous to you, you're at the beginning of the sequence, right? And so the model can kind of like figure out that it's at the beginning of the sequence. And so that slips into the transformer as you add more layers to the transformer. So even models trained with rope don't extrapolate perfectly to really long sequences, but they work better than models trained with other varieties of encodings. Okay, cool. Next, I want to go to layer normalization and residual connections. So one of the big problems that I pointed out last time was vanishing gradients. And so in RNNs, we talked about how backprop through a network causes gradients that can vanish or explode. And so if we backpropped through a network that had a simple RNN, by the time we got to the beginning, we would have gradients that were tiny, for example. Actually, I'm really sorry. I forgot to mention something that's really, really important, which is if we look at these transformer diagrams, actually, we can just look at this one here. So we have a transformer. A transformer consists of a block of mass multi-head attention, layer norm, which I'll talk about in a second, and then a feed-forward network and layer norm. But we repeat this over and over again. So we repeat this for like 8 layers or 16 layers or whatever else. So we actually have a very large number of these kind of transformer blocks included in here. And so what that means is like in RNN that processes a very long sequence, we now have many different transformer blocks that we're backpropping through before we get to the beginning of the sentence. Sorry. Before we get to the beginning of the model as we backprop through layers. And so there's 2 ways we fix this. The first way that we fix this is through something called layer normalization. And the way layer normalization works is it normalizes outputs to be within a consistent range, preventing too much variance in the scale of the outputs. So just to give an example, like let's say we had a value vector or a value matrix where all of the elements in the value matrix were kind of like 10,000 or something like that. That would mean that after we ran through mass multi-head attention, if our inputs were between 0 and 1, or between like -1 and 1, or tended to be in that range, after we put them through multi-head attention, we would have things that were between -10,000 and +10,000. And that's a big problem, for the reasons that I mentioned before. Like if the scale gets very large, the softmax gets very peaky, like other problems like this. This hurts learning, this hurts performance. So what layer norm essentially does is it normalizes for this so that we keep values in a similar range. And so it looks like this. This is the mean of an input vector, x. This is the standard deviation of the input vector. And we have a bias here and a gain. And so what the mean does is it takes things that might be shifted very far from like being zero-centered and moves them back to be zero-centered. The standard deviation takes things with like a very large scale or a very small scale and makes them have a standard deviation of essentially 1. The gain makes it possible to move, to readjust the variance. So like maybe we want the variance to be large, in which case we could have this gain and we would have the variance be large on average. And then finally, the bias allows us to move back away from being zero-centered. So basically what we do is we pull things in to be zero-centered. We make them have essentially unit standard deviation. Sorry. What's that?
Zero mean.
Yeah, zero mean and unit variance, sorry, not standard deviation. And then we readjust the mean and the standard deviation. So that's what layer norm does. So that allows us to control kind of the scale of the vectors that we get. Another popular variety that's used pretty widely now is something called the RMS norm. And RMS norm is not, it has the same objective as layer norm, but it aims to be more simple. And so it essentially just removes the mean adjustment. And so it takes something that looks like the variance and just divides by the variance and multiplies by a gain. So it doesn't do the mean adjustment. Yeah, and I should point out the overall performance using RMS norm or layer norm are approximately similar. So the only main reason to use RMS norm is that it gives kind of fewer parameters and simpler, faster. The next thing is residual connections. So residual connections, as I talked about, yeah, sorry, go ahead.
Yeah, so when you're doing layer norm or RMS norm, is there a risk that you run where you don't have the diversity of the words represented exactly? Like when you don't do layer norm and you have the problem of exploding or vanishing gradients, you can see the range of like similar words being like a really high value and not so, or words that you haven't seen much being a much smaller value.
Yep.
When you compress it down to a certain range of say 0 to 1, is there a loss of information that you are able when you do that?
Yep. Is there a loss of information when we use layer norm? Definitely yes. So you can tell there's a loss of information because all.
You can always go back. So how would it have been lost information?
Well, okay. Let me give an example. These will be the same after layer. So we're losing the ability to determine between things that have the same like spread profile, because the mean will be subtracted. The variance is the same, and when we re-add the bias is independent of the input vector. So even if the bias was like 2, 3. Both of those vectors would become 2, 3 in that. So we're definitely like losing information because it's not a bijective function basically. Yeah.
Train for the gain or is it constant?
Yeah, you train the gain in the bias. Yeah. Cool. Okay. So next, residual connections. So as I mentioned, in LSTMs, the reason why we added additive connections between each of the steps was because we wanted to avoid vanishing gradients. So residual connections are basically the same thing as we go through layers of the network. And so every time we do any sort of modification, we do multi-head attention, layer norm, or sorry, we have 2 residual connections within the transformer block. We have one from here to here and one from here to here. This prevents vanishing gradients. And kind of another intuitive way to think about it is if we didn't have a residual connection, this mass multi-head attention would need to learn kind of to pass all of the information. But what it has to do instead is it has to pass only the difference in the information, only the information that you want to add to the previous vectors. And that's actually part of it. It kind of explains why in self-attention we would see an example like this. So normally you would expect the meaning of the word making would be mostly influenced by the word making, right? You know, making is making, regardless of, you know, the surrounding words. So we would want to pass most of the information from making to making. But we don't see that in the attention patterns. And the reason why we don't see that in the attention patterns is because this gets the meaning of making for free through the residual connection. So it only needs to pull in like the change of information that you get from the surrounding context. And so in well-trained transformer models, things will not attend to themselves that much in self-attention. So this is a really important difference, post-layer norm versus pre-layer norm. So these are two examples of post-layer norm and pre-layer norm. The way that post-layer norm works is you do layer norm after you do the residual connection. Pre-layer norm, you do layer norm before the residual connection. And before the input here. And so the reason why this is really important is actually, if you look at this, there's no residual connection that goes all the way through the network. So this residual connection basically gets, the output of the residual connection gets modified every time by layer norm. And so this means that it's actually more difficult to pass information all the way through all of the layers. But for this one, you can see you have a residual connection that just goes straight through the entire network. And because of that, it's much easier to pass a gradient all the way from the beginning of a deep network to the end of a deep network. And because of this, pre-layer norm is better for gradient propagation, and this is often favored in recent models. One difficulty, as always, is if you're passing things directly through, it can cause exploding gradients. But in general, this is favored. Cool. Any questions about that? Yeah.
In the previous slide, if you just apply the layer norm before the addition, would that have
The layer norm before.
the addition?
Yeah. So that could be post layer norm within the residual connections. You can do that too, but these are all variants. I think I've not seen a lot of people doing that particular variant, and I'm actually not 100% sure why, but yeah. Cool. Okay, so let's move on to feed-forward layers. Feed-forward layers are basically the same as feed-forward layers previously. They extract combination features from the attended outputs. So what we do is we calculate a linear transformation and nonlinearity, multiply it by weight, add a bias. And usually these feed-forward layers are very big. They're much bigger than the actual vectors themselves. And the reason why is because you want to extract combination features that combine, you know, multiple of the hidden layer features. And so these tend to be, you know, quite a bit bigger, like 4 times bigger or something like that than the original ones. So in transformers, different models use different activation functions. So I talked basically very briefly about activation functions before, like tanh or sigmoid. In the original transformer, people have tended to use ReLU. And ReLU is a function like this. It's basically 0 if you're less than, if the input is less than 0, and the input itself if it's greater than 0. Now, in LLaMa and other similar things, it uses something called Swish or SILU. And the way this works is it's very similar to a ReLU, but it drops down a little bit. and then goes up. So it's like a differentiable version of a ReLU. And actually, sorry, I don't have this in the slides, but when this is combined together, there's a gating function. And when it's combined together with a gating function, it's called SWGLU for like a gated CILU, basically. And that's widely used in LLaMA and other things like this. So this one, the reason why they switched from ReLU to SWGLU or CILU is because this is not differentiable at all. So you don't get any gradient when it's less than 0, or it's differentiable, but it's constant. And so this is differentiable, so it gives you some signal there. Yeah. Okay, cool. So a next thing that I'd like to talk about is optimization tricks for transformers. So transformers are powerful, but training them can be a bit unstable. And so if you want to find an interesting example of how difficult this was, at least traditionally, this logbook is from one Meta trained an older 175 billion parameter model. And basically, this is an open source model that they trained, and they basically released their whole logbook of training. And they, at the very end, they have rainbow colored done training because they were very happy about it. But you can go through and you can see all of the trouble they had getting this thing to converge, and how they had to wake up their sysadmins late at night because their cluster had crashed and other stuff like that. So it's very interesting to read. It also makes you feel better as a graduate student where all of your model training is not working well. So, actually, this is older, and recently, a lot of people, Meta included, have kind of gotten better at training models. So you can train much more stably than is written in this logbook recently. So optimizers for transformers, as I mentioned before, Atom is kind of a standard optimizer nowadays. And just to recap from last time, it's like SGD, but we have a momentum term and a momentum term for both the mean and the variance of the gradients. When training transformers, it's very, very common to have a learning rate schedule. And this is kind of the classical learning rate schedule. There are small variants on this, but they all kind of follow a similar pattern, where basically you have a warm-up stage. In the warm-up stage, you gradually move the learning rate from 0 to a larger value. And then you have a cool-down stage. And the cool-down stage basically gradually lowers the learning rate. And the reason why you have the warm-up is if you start out with a very big learning rate, the first several steps of a transformer, like the atom parameters, the atom momentum has not been populated. And you can basically very quickly get into a bad space in the parameter space, and you'll have a model that's not very good. The cooldown stage is because as the model gets more trained, you want it to not jump around quite as much. You want it to kind of settle into a good minimum. Another thing I should mention is that actually in LLaMA 3.1 and other similar models, they have something that they further call an annealing stage, where at the very end of training, they like drop the learning rate down to 0. And so they go up, they cool down, and then at the end, they cool down like all the way to 0 to kind of make the model as stable as possible at the end. So that's a rather new development, so new that it didn't get on my slides. So Atom W is something that adds weight decay to Atom. And the basic idea behind weight decay is weight decay gradually reduces the weights of the network. And the reason why you want to do this is essentially adding regularization to the network. It's trying to reduce the very big weights. And this is equivalent to adding basically L2 regularization, if you're familiar with that from a machine learning class. And but it's kind of tricky to add this weight decay to atom. You can't just like decay the weights because that would not result in it being equivalent to L2 regularization. So essentially atom W properly applies weight decay for regularization. And this is another thing where I'm not going to go into the equations on the slides, but you can read through the paper to understand that. Okay, next. Low precision training. This is really important. And the reason why it's really important is because GPU memory is precious. And if you're training on GPUs or other varieties of hardware, in training very large models, you'll very quickly run out of memory. And so training at full 32-bit precision can be very costly. There's a number of low precision alternatives, and I already talked about this a little bit last class. But basically, the standard IEEE half precision, this is a 16-bit float instead of a 32-bit float, allocates 5 bits for the exponent. bfloat 16 allocates 8 bits for the exponent. And recently, this has been very favored in training models because it's more important to have things with a very large range, like weights with a very large range, than with very good precision, because you're using stochastic gradient descent anyway. Things are going to be wobbling around, and the range is more important. I actually heard that a lot of the instability in the OPT training log was due to the fact that they were using FP16 instead of bfloat 16. So that has reduced, using this properly has made training a lot more stable. Okay. Any questions so far? Yeah. Yeah, I think all of the major libraries support bfloat 16. Cool. And to follow up on that, I think many models have checkpoints in bfloat 16 already. If they don't, you'll have to convert it and then run.
And like LLaMa or LLaMA from 1 to 3. I think LLaMA 2 and 3 use the bfloat 16 for training.
Yeah, and then I think they have the original checkpoints are bfloat 16, and then there are like always converted checkpoints into other varieties. So. Okay, so checkpointing and restarts. This is also tricky. This is especially tricky if you're doing pre-training, but it can also be tricky even if you're just fine-tuning models. So even through your best efforts, training can have problems. So what you want to do, ideally, is monitor possible issues. The one standard thing to monitor is the norms of the gradients. And so this is your perplexity. And often you will see something like this. Perplexity, as we talked about before, is kind of like language modeling performance. And it will be going down. And then suddenly you have like a spike, and then it continues to go down and train kind of like okay. But then suddenly it gets a lot worse. You can also see the norm of the gradient, and the norm of the gradient spikes. And then after the norm of the gradient has spiked, your model has gotten in a weird place because it suddenly had a very large gradient, which messed up, the parameters themselves, also the atom momentum, other things like this. And your model is dead here, but you don't realize it's dead until like a lot later. So also, sometimes you don't even get the big perplexity spike here. You would just see a gradient norm spike, and then things die. So this is an important thing to be monitoring if you're training, especially if you're training large models. So that's a good thing to know. If you have training crashing, rolling back to previous checkpoints, shuffling data and resuming is the best way to do it. And you usually will want to roll back to a checkpoint that's like well before the gradient spike, because the gradient spike happened, like you don't want to roll back to directly before the gradient spike and then use the data in the same order because it's just going to happen again. So you want to roll back quite a bit. You can shuffle the data or skip some data or something like that and then resume training, and that will help prevent it from happening. But another really important thing is to check your code. Because like a lot of times when you get a NaN in training or a gradient spike or something like this, it's because kind of an edge case has happened in your code. So just to give some examples, let's say you have some function where you're dividing by the sum of a vector. So this is super, super common, right? Dividing by the sum of a vector. You might do that if you are for example, applying RMS norm or gradient norm, right? This is the sum of a vector and you're dividing by it. But what happens if your vector is 0? You suddenly get something very large. Or if your vector is very close to 0, you get something very large. So this happens almost never, because, you know, when is your input vector 0? When are all of the elements in your input vector 0? Almost never, right? You know, it's not going to happen much. Unless all of the inputs to your ReLU are negative. So if you're using a ReLU and you're using layer norm and all the inputs to your ReLU are negative, they all become 0. You divide by 0 and it spikes. And this, as I said, happens almost never, but it will happen in your 120,000th step of training your very large model, and then your model dies, right? And so there's usually a reason why you're getting NANs. It's not just like because your processor failed or something like that. It's usually somewhere in your code, but it might be somewhere very rare. So if you're seeing NANs, you need to be suspicious of things like dividing by 0 or feeding a negative number into a 0 or a negative number into a log or something like that. Anything that could create an infinitely large or infinitely small value. Cool. So one final thing that I'd like to finish up with is if we look at the original transformer versus LLaMa, LLaMa is an architecture that is very popular. It's also used in many, many other language models. Like a bunch of people have copied the LLaMa architecture. And there's important differences between it. These are the biggest ones. The first one is the original transformer used post-layer norm. LLaMa uses pre-layer norm. The norm type is layer norm versus RMS norm. The nonlinearity is ReLU versus SILU or SWIGLU. And the positional encoding is sinusoidal versus rope. And these are the main differences between the architectures. Of course, there's like sizes of layers and other things like that, but these are the main architectural differences. And this is really important. So a lot of people say things like data is all you need, like data is the only thing that matters. I would argue that it's not that data is the only thing that matters, but it's that we picked most of the low-hanging fruit of like architecture engineering by using the LLaMa architecture. And as evidence of this, this is from a paper that introduces an alternative architecture called Mamba by Albert Gu here at CMU. But the one interesting thing from this figure is not the Mamba comparison, but the transformer plus transformer plus plus comparison. The transformer is basically the Vaswani et al. Original transformer from 2017. The orange transformer plus plus is basically LLaMa. And these have the same number of layers. They have the same, they have the same number of layers, and like all the other decisions are more or less the same, but kind of the architecture and some of the learning rate stuff is modeled after LLaMa. And you can see that this makes a huge difference. So like training on 1/10 as many flops gives you about the same performance using this more efficient architecture. So it's not just scale, it is the architecture that makes it better. Cool. Actually, I think I will skip that part for applications. But I would like to talk a little bit about mini batching or batching. And batching makes processing much, much faster, especially if you're doing it on GPUs. And the way it works is you essentially pad sequences to make them the same length. So you take multiple sequences, you put them in a single batch, and then you pad them together to make them the same length. Do appropriate masking to make sure that you're masking out any of the, padded sequences, and calculate loss and take the sum of them. And this is done under the hood for you in, PyTorch or whatever else you're using. You can just do it when you create batches using their data loader. But the important thing to know about it is if you batch things of very different lengths, you will you can have issues. So for example, let's say you have 3 sentences of length 2, and then 1 sentence of length like 30. The resulting batch thing would have 28 tokens worth of padding for each of the short sentences. And this is an issue because it would be wasting lots of computation, wasting lots of memory, other things like this. So it's important to be aware that this batching is happening, or this padding is happening. Another thing to be aware of is that there's a way to manage this, and a way you can manage this, or there's kind of 2 ways you can manage this. One way you can manage this is if you're using sequences of different lengths, too much padding can result in decreased performance. So one remedy for this is sorting sentences and making sure that you use sentences of similar lengths in one batch. Another option, which is mainly used in pre-training, maybe used a little bit less when you're doing instruction tuning, is to just ignore document boundaries and concatenate things together. So like you have things from document A, and then you have the end of document thing, and then things from document B. You have end of document, things from document C, and then your next batch would be like the remainder of document C, etc. So that makes sure that like all of the sequences are similar length. There's no padding involved, but it gives you weird things on the document boundaries, so you might lose context and stuff like that. So those are the 2 main methods that people use to handle that. Cool. Yeah, I think that's mainly what I want to cover today. The final thing that I want to cover is there's a really good reference called the annotated transformer. And the annotated transformer is basically what this was created by Sasha Rush and others. And it goes through the whole transformer paper. And you can read the transformer paper, and then as they go through the transformer paper and have the description of the architecture, they have the code in PyTorch. So you can kind of follow along with everything and understand it really well. So this is included in the references. I'd highly encourage people to take a look at this if you want to read more. So.